There's never been a stranger idea in the entire history of science. Down at the smallest scale, smaller than our cells, smaller than atoms, could the world suddenly get bigger? Branching out in new and totally unexpected ways? A quest to understand the ultimate nature of reality has gripped the greatest living minds and is forcing us to consider a truly shocking possibility. Are there more than 3 dimensions? Space, time, life itself. The secrets of the cosmos lie through the wormhole. Up, down, backward, forward, side to side. If you want to get anywhere on Earth, these 3 dimensions are the only ways you can go. They describe any place in our reality. Or do they? Many scientists now believe our world is not 3-dimensional, that somehow there are other ways to move. Discovering those hidden dimensions is the biggest prize in physics and would forever change the way we see the universe. When I was a boy down in the Mississippi Delta, bugs swarmed all summer long. Some of them could even walk on water. But down below, there were creatures who would occasionally dart up and grab an unsuspecting bug. The water bugs never seemed to see it coming. Why not? Was it because to them the pool had no depth, no 3rd dimension? Could we be like water bugs, unable to see the full extent of reality? Susan Barry knows all too well the limits of human perception. She was born with her eyes severely crossed. As a baby, her brain's attempts to fuse the separate 2-dimensional images from each eye into one 3D image ran into serious trouble.
Now, when I was little, being cross-eyed, if I, let's say, looked at the apple with my right eye, my left eye would be turned in and looking at something else, let's say this clock. So that would mean one eye is seeing the clock and one eye is seeing the apple. And the brain might interpret that to think that the clock and the apple were in the same place in space. Now, if you think about that, that's an untenable situation. Because how would you be able to know how to move and interact with things if you don't know where they are in space? So if your eyes are crossed like that, you have to find a way to adapt. And one way to adapt, the way that I used, was I simply threw out the information from one eye, the eye that was turned.
Susan had eye surgeries when she was a child, but they only changed her outward appearance. She could only see 2 dimensions. Nothing had any depth. Everything, even her own reflection, looked entirely flat. And it seemed she would live that way forever.
For the past half-century, there has been a belief that if you did not develop the ability to see in 3D within the first years of life, in early childhood, you could not develop it as an adult.
And while you're looking at the...
But in her late 40s, Susan began a rigorous vision retraining program to try to teach her eyes to lock onto the same target and give her brain the chance to discover an extra dimension of space. One day, after her 48th birthday, something incredible happened.
I went out to my car, and I sat down in the driver's seat, and I went to look at the steering wheel, and it had popped out. It was popped out in space with this palpable pocket of space between the steering wheel and the dashboard. And I had never seen anything like that. And all that day, my stereo vision would emerge like intermittently, unexpectedly. And it would be amazing. The sink faucets were really jutting out toward me. And I can remember just admiring the sink faucets and thinking that I had never seen an arc as beautiful as the arc of those sink faucets.
The sudden appearance of this extra dimension was a revelation to Susan Barry. But the idea that another dimension beyond the 3 we know might be hiding from all of us is now at the center of the world's most important scientific investigations. Harvard professor of physics Lisa Randall is at the forefront of this hunt. She sees the world differently from you and me.
It was just one day I was walking to work, and I realized I really did think that extra dimensions could be out there.
The main reason for her conviction that there must be more than 3 dimensions? this paperclip.
It's really strange. If I take this tiny magnet, I can pick up this paperclip, even though the entire Earth is pulling down on this paperclip. If you think about it, the force of magnetism that is exerted on this paperclip is enough to compete and actually overwhelm the force of gravity that's acting on it. So there's a mystery there, because why is electromagnetism so much stronger than the force of gravity?
Physicists have discovered that we live in a world governed by 4 primal forces. There's electromagnetism, the force that affects objects with electric charge, the strong nuclear force, whose power is unleashed in nuclear weapons, and the weak nuclear force that triggers radioactive decay. These first 3 forces are all roughly equal in strength, but the 4th force, gravity, is much weaker. In fact, it's around 1 trillion times weaker than the other 3.
So we're trying to understand what can explain why gravity is so much weaker than the other elementary forces. And one of the possibilities that we've started to think about quite seriously in the last decade or 2 is that there could actually be additional dimensions of space. If that's true, it could be that gravity is weak because it's actually concentrated somewhere else in another dimension.
The idea that extra dimensions might be a hidden part of our reality is as old as Plato. He imagined the world we live in to be like the wall of a cave lit by firelight. Shadows dance across our 2-dimensional world, cast by objects in the body of the cave in a 3rd dimension that's hidden from us. A 3-dimensional geometrical shape, like the tetrahedron, which has 4 equal sides, could cast a distorted shadow on the wall so that one side looks much shorter than the others. Just as an extra dimension can hide the true length of one of the sides, so too it might be hiding the true strength of gravity. And Lisa Randall's efforts to learn about extra dimensions begins, like Plato's, with studying shadows.
So here I have a 3-dimensional cube. Now, if I had a single projection, I might actually confuse that, for example, of just being a square, which is 2-dimensional. However, by rotating the object and looking from different angles at different projections, you can tell that what you have is a 3-dimensional object. By putting together the information, you can deduce what's there.
Just as a 2-dimensional shadow can help us learn the true shape of a 3-dimensional cube, we can explore a 4-dimensional cube, a hypercube, by looking at its 3-dimensional shadows.
Or we can look at different projections of a hypercube. What we would see are things that from one angle it might look like a cube. From other angles it might look like a cube inside a cube. It might look like it's turning itself inside out because we're not really in the 4th dimension. So it does things that we're not familiar with because it has this whole other dimension of space that it can play with.
But if a 4th dimension does exist, shouldn't we see objects changing shapes like this, even turning themselves inside out? Could it be that whatever exists in the 4th dimension is somehow blocked from entering our world? Or could they be hidden some other way?
So if there are extra dimensions, they have to be pretty well hidden for us not to have seen them. So why would that be? It could be these other dimensions are just so tiny we just don't notice them.
But this scientist thinks he's discovered a new way to detect them, and that dimensions we can't see control the way everything in the universe moves. What would it look like if we were to travel into a 4th dimension of space? It's not easy to imagine. But here's one way to get an idea. Think of the palm of my hand as a world of only 2 dimensions. If a 3-dimensional ball were to pass through it, what would the inhabitants of my palm see? A circle that grew and then shrunk down to a dot before disappearing. So, if I could move into the 4th dimension, my 3-dimensional projection would distort, shrink, and finally flicker out of this world, becoming totally dark. UC Irvine physicist Tim Tate thinks most of the matter in the universe may have moved into the 4th dimension and gone dark. He too spends most of his time trying to escape the dimensions that normally confine us.
When you scuba dive, you become immediately aware of the fact that you have to control how high you are, how deep you are in the water, how close you are to the surface. And so you instantly become aware of the fact that there's another dimension in a way that you can't really feel when you're on the ground.
Tim believes that yet another dimension, a 4th dimension, might be the key to explaining one of the deepest mysteries of the universe, the mystery of dark matter.
In the recent years, we've become really aware of the fact that when we account for all the stuff in our universe, there's stuff that's missing. We can see it pulling on other things gravitationally, but other than that, it doesn't leave any trace that it's there.
Scientists are convinced dark matter exists because it's affecting the way stars rotate around galaxies. The gravitational pull of it is so strong that they estimate dark matter outweighs normal matter by 5 to 1.
We really don't know what dark matter is, but there have been many ideas that have been proposed to try to explain it. And my own personal take on dark matter is a theory with extra dimensions.
Tim's idea is that dark matter could be evidence that a fourth dimension exists, a dimension that is almost impossible for us to see.
So an analogy for the extra dimension would be looking at the anchor line of a boat. When you look at the line from far away, you see a line. You see a long, thin object, and you don't realize that it actually has width, that it has an extra direction that you can move if you were sitting on the surface of it. Close up, it's actually a cylinder. It's big and fat, and you can move around the periphery of it.
If particles were moving around this cylinder, and if it was small enough, they would look to us like they were not moving at all.
So this is our model for an extra dimension. We have the bob, which represents a particle. As I spin the particle around, it goes in a circle with a string holding it in place, and that represents it moving in the extra dimension. So let's see how that works. So here we have it spinning around in the extra dimension. As it gets closer and closer, it speeds up, it moves faster and faster, and has more energy. Even though this particle looks like it's standing still, it can actually be moving very, very fast, just in a very, very small circle.
Any particle that is moving must have energy, and according to the most famous equation in all physics, if you have energy, you have mass. That gave Tim a flash of inspiration about what dark matter particles might actually be, and how they might lead us to discovering the fourth dimension.
So photons are particles of light, but if there's another direction that photons can travel in, we can actually get a dark matter particle by just taking these massless photons and letting them move around in a circle in the extra dimension.
If Tim is right, dark matter is actually made of light. Massless particles that appear to have mass because they are racing around a tiny fourth dimensional loop that's too small for us to see. But how and when did these photons leave our three-dimensional world and enter the fourth dimension?
One way you can try to understand this is if you think about a roundabout in a playground. It's spinning around really fast. To actually get onto the roundabout, a child is going to have to run around it at the same speed that it's spinning. But if it's spinning faster than the child can actually run, then there's no way to get onto it safely. Most particles we have today just don't have that much energy. But when the universe was very young, it was very small and it was very hot. And at that time, particles had a lot more energy, and they were able to actually get into the extra dimension.
Right after the Big Bang, super high energy particles of light may have blasted their way into the fourth dimension. They've been stuck there ever since, and appear to us today as dark matter. But Tim thinks there might be a way for them to get out. And when they do, they could bring us proof that the fourth dimension really exists. If two photons are moving around this curled up dimension in opposite directions, they might occasionally bump into one another. When they collide, they annihilate and burst out as an intense shower of energy into our 3D universe. Even though this event is rare, these collisions in the fourth dimension should create a telltale signal.
Engine start. Liftoff.
In 2008, NASA launched the Fermi Space Telescope, a probe designed to pick up the intense radiation, gamma rays, created by cosmic cataclysms like exploding stars. But it should also detect gamma rays from dark matter photons as they annihilate one another.
So as it collects data, we understand the gamma ray sky, and we start to look for where the dark matter might be.
Fermi has already discovered a sea of gamma rays emanating from the center of our galaxy. But much more work is needed to prove this signal is coming from the fourth dimension.
So obviously I hope that tomorrow we declare victory and explore the extra dimension. On the other hand, I don't know exactly when we're going to discover it. I think, though, that the prospects today are much better than they have been in the past.
The Fermi Telescope will continue gathering evidence from the depths of space until around 2015. But proof that there are more than three dimensions may not come from so far away. Right now, the biggest experiment mankind has ever built is trying to find them under the Swiss Alps. The goal of science is to reveal to us the deepest workings of nature. And nothing in science attempts to go deeper than string theory. String theory says that Every single particle of matter and energy in the universe is actually a tiny vibrating string. A string that vibrates not in 3 dimensions, but in 9. If string theory is right, at every point in space there are 6 extra dimensions, curled up incredibly tight. These hidden dimensions could solve all the mysteries of physics. But there's a problem. Since string theory was first proposed over 40 years ago, there's not a single shred of evidence to support it. Thousands of scientists are on the hunt for that evidence. Under the foothills of the Alps in Geneva lies the Large Hadron Collider, the LHC. It's a 17-mile-long circular racetrack designed to smash subatomic particles together at phenomenal energies. Caltech physics professor Maria Spyropoulou has been working at the Atom Smashers in Geneva since she was an undergraduate. She has seen trillions of particles fly like subatomic shrapnel through the detectors.
The LHC, I think it is the most ambitious and technologically complex scientific project that humanity has ever attempted. We got 1 billion collisions per second, and this is a daunting task to record this data.
Maria and her colleagues have sifted through this immense pile of data and identified dozens of tiny subatomic particles, the basic building blocks of matter. But they've never seen the strings that lie at the heart of each of these particles. String theory predicts that they must be 1 trillion times smaller than an atom. Put that another way, if an atom were the size of the solar system, a string would be the size of a light bulb. And the smaller an object is, the more energy it takes to see it. The energy of the subatomic particles racing around the LHC is staggeringly large. Protons zip around this ring so fast that a beam of light only outruns them by about 8 miles an hour. But to see fundamental strings and their 6 curled up dimensions requires levels of energy almost beyond comprehension.
If you want to make a collider that will actually produce something like strings, it would take an accelerator much bigger than the LHC, much bigger than the Earth, the circumference of the Earth, possibly much bigger than the Milky Way.
But there may be a way to prove that string theory and the 6 extra dimensions of space that come with it is correct. A way that does not require seeing tiny strings directly. Joe Polchinski is one of the world's leading string theorists. Like many physicists, he draws inspiration from being close to nature.
It's great to get out here in nature, in the mountains, to think about things a bit. When you get to the top of a climb, you really get a much bigger picture.
Joe has probably delved deeper into the workings of string theory than anyone else, and in doing so, he realized something crucial was missing from the math.
So we know that the basic building blocks of nature have to be really small. Smaller than anything we've ever seen, probably a whole lot smaller. So if these building blocks are strings, they're very elusive. How do we know that they're there? And so it's challenging. And there was this one calculation we would do, and the answer that the math was giving us wouldn't match up with the physical picture we thought we had. It turned out that the problem was the strings themselves were not enough. What the math was telling us was there was another kind of thing, another sort of object in the picture.
In 1995, after many years of work, Joe made his way through the tortuous math and discovered the source of strings. He called these objects D-branes.
So we're out here on this nice hike out here in nature, and we've got this beautiful spider web, which is a nice model for some of these ideas. So D-branes are these higher dimensional objects. They could be 2-dimensional, 3-dimensional, or even more. And this spider web is 2-dimensional, a nice sheet. And it, like a sheet, it can flex and bend the way D-branes can flex and bend. Now, it's not a perfect model because this web is stuck between these 2 branches, but the D-branes can go on forever. They could be of cosmic size, stretching from one side of the universe to another. And if you look close, you see that there are these little bugs stuck to it the way strings get stuck to a D-brane.
In Joe's theory, D-branes could take on any of the 9 dimensions that exist in the mathematics of string theory. Our entire universe could be a 3-dimensional brane, a block of space to which all the strings, all the matter in our universe, is stuck.
Now you have the brains doing what they do. And you find that very possibly the dimensions could be much larger than we thought about. Large enough to see particle accelerators, large enough to maybe have effects on what we see in astrophysics, in some of the physics we see from space.
Thanks to Joe's discovery, scientists around the world are fueled with fresh hope that they may soon detect extra dimensions. If you, me, every star, every galaxy in the cosmos is stuck on a three-dimensional brain, then a fourth dimension wouldn't have to be a tiny fraction of an atom. It could be much bigger. The discovery of extra dimensions would be one of the biggest breakthroughs in the history of science, but it might also spell disaster, because the experiment that proves they exist might also create a black hole here on Earth. In 1609, Galileo peered through his telescope and spied the moons of Jupiter. His discovery of those four tiny points of light, invisible to the naked eye, changed our understanding of our world. Extra dimensions of space will be much harder to see than Galileo's moons. But if we discover them, it will change our understanding of the entire universe. This piece of delicately balanced equipment could be the device that discovers the fourth dimension. It sits in a basement at the University of Washington and belongs to this man. Eric Adelberger, along with a small team, has spent the last decade watching this torsion balance twist back and forth, hoping it reveals evidence that there are more than three dimensions.
Gravity is really an amazing story. It was the first of the fundamental forces that the physicists learned about. Isaac Newton had his theory of gravity, which has been tested very well in the solar system, but it's not really been tested very well at all at very short distances. And these short distances are now where all the theoretical action is, so to speak.
The forces Eric needs to measure are incredibly weak. Even though the lab is underground, his data is frequently marred by trains, rush hour traffic, even airplanes flying miles overhead.
The forces we're measuring are really extraordinarily tiny. To get some idea, if you could cut a postage stamp into 1 trillion little pieces somehow, and could weigh one of those little pieces somehow, that's the kind of forces that we're measuring.
If the force of gravity deviates from Newton's laws at very small distances, it would be a telltale sign that an extra microscopic dimension exists. It's a principle Eric knows firsthand from his passion outside the lab, tending another set of delicate objects.
The nice way to understand this is this analogy between the way gravity spreads out in varying number of dimensions and the way flow of water spreads out in varying number of dimensions. We've got a steady stream of water that flows out of these two outlets at the top, falls into a channel and is confined in one dimension, and it runs down along in one dimension. And we've made one channel twice as long as the other channel. And we're going to measure the flow of water by watching how much the level of the water in this bucket changes compared to this bucket, where the water's had to travel twice as far in that one dimension. The amount of water that's flowed through the longer one-dimensional channel is just the same as the amount of water that's flowed through the shorter one-dimensional channel. So what this tells us about gravity is that if gravity were operating in a one-dimensional world, it would be the same if objects are close together or if they're very far apart. So now we're going to see what happens when the water flows in two dimensions. In our two-dimensional experiment, the beaker that was closer to the water source got twice as much water as the beaker that was farther from the source. If these two beakers here were our measure of gravity, we would know that we were in a two-dimensional world because we got twice as much water over here. Okay, now we're going to see what happens when the water spreads in three dimensions.
When water spreads out in a three-dimensional world, when you place the bucket twice as close to the source, you get 4 times as much water.
So if we lined up the beakers from the three experiments, we'd see that the 1D beakers, the water was the same height. 2D, the nearer beaker had twice the water, and in the case of 3D, it had 4 times the water. Now, if we could imagine that we were living in 4 dimensions, what would we see? We would expect to see that the nearer beaker had 8 times the amount of water that the more distant one had.
The more dimensions there are, the faster the force of gravity changes with distance.
Well, we've measured gravity down to roughly 50 microns. That's about half the diameter of a hair on your head, okay? So far, Mr. Isaac Newton is still correct.
If Eric can get even closer, the hidden world of extra dimensions could suddenly pop into view.
There are reasons to think that, the region between 50 and 10 might contain some real surprises. And of course, that's stimulating our enthusiasm for doing the experiments.
On the other side of the planet, at the Large Hadron Collider, particle physicist Maria Spyropoulos is also looking for unexpected changes in the force of gravity. But if her experiment is successful, she'll create something never before seen on Earth, a black hole.
It is quite possible the LHC experiments can produce the so-called microscopic black holes.
This is not the type of black hole that is born from a collapsing star, where the core gets so compacted that nothing can escape its gravitational pull. What Maria is looking for is evidence of a microscopic black hole. If the LHC can force two particles sufficiently close together, and if extra dimensions are large enough, gravity could start growing much stronger than expected, eventually compacting the two particles enough to form a tiny subatomic black hole. But don't worry about moving to Mars just yet. The black holes Maria and her colleagues expect to create are tiny, so tiny that they will evaporate in a fraction of a second.
The microscopic black holes, as soon as they are produced, they immediately decay with a very, very short lifespan. There is a spray of these particles, and that is the clue that such an object might have been created.
The LHC has been looking for these black holes for over a year. So far, they found no hint of even a single black hole being created. Extra dimensions remain elusive. But Lisa Randall thinks that might be because they're different from what most scientists expect. She believes extra dimensions are warped and that they are passageways to a parallel universe. Extra dimensions are not easy to see. If they were, we'd have found them long ago. Many scientists now believe we'll never have the technology to find them. But extra dimensions might still reveal themselves, because they might be separating us from a parallel universe. An entire cosmos could be lurking less than a trillionth of an inch away. Harvard professor Lisa Randall has a radical new idea about extra dimensions, one that will change the way we see our entire universe. She began with string theory, the idea that all the fundamental particles are just vibrations of tiny, nine-dimensional strings. Then she added in Joe Polchinski's ideas that strings making up all the stuff in our universe had to be stuck to a giant three-dimensional object called a brain.
There are two types of strings, strings with ends and strings that are closed loops, like rubber bands. And the strings with ends, those ends, have to be somewhere. They can't just be anywhere in higher dimensional space. They have to be on the surface of a brain. And if that's true, the particles associated with that string will also be on the brain. And it turns out that all the matter we know about, and also the forces through which they interact, might all be stuck in a brain through this mechanism, except for gravity, because gravity is never associated with open string. Gravity is associated with a closed string. And closed strings have no ends. There's no mechanism that makes it stick to a brain. A closed string can be anywhere.
Lisa's math suggested that gravity might be so weak because the closed-loop strings that carry this force, gravitons, are being pulled away from our brain and concentrated instead in a parallel universe that's separated from us by a fourth dimension.
You can imagine that these two buildings behind me represent two different brains. And we maybe are living only in that building or that brain. If gravity is concentrated at the other building, we might only get a tail end of gravity. It might be that that could explain why gravity is so weak for us.
Gravitons flow freely between our brain and the one that's across the fourth dimension. But the gravity in that parallel world is so strong it compresses space trillions upon trillions of times smaller than ours. The space between these two brain worlds is warped. As gravitons move from the dense gravity brain to our brain, they spread out and their force gets far weaker.
Things get rescaled as you go from one place in an extra dimension to the other. So whereas things might be extremely heavy here, they could be exponentially lighter here, which would naturally explain why gravity is so weak.
Lisa Randall's idea of a warped fourth dimension separating us from a parallel universe where gravity is just as strong as the other forces of nature has set the world of physics alight. Back at the Large Hadron Collider in Geneva, the beams will soon be smashing together with enough force to produce particles that could prove this warped dimension really exists.
Well, if this idea is right, you would actually be able to make particles that essentially have momentum in another dimension. Now, we don't see that other dimension. What we see is the effect as if the particle had mass, and the mass turns out to be the right mass that it can be produced at the energies of the Large Hadron Collider, we hope.
Any day now, news may come from the Swiss Alps that the world is fundamentally different from the way we've always imagined it. But there is one more twist to this epic hunt for warped or curled up extra dimensions. One scientist thinks our search is doomed to failure. She does not believe there are more than 3 dimensions. She thinks there's only one. How do you build a universe? Do you need 3 dimensions? Or do you need 4, 9, or more? These are the most fundamental questions scientists can ask about our reality. But the simplest questions are often the hardest to answer. Swarms of scientists at the Large Hadron Collider and labs around the world are hunting for evidence of extra dimensions, be they warped or curled up in tiny loops. They hope to make a major breakthrough within the next few years. But Renate Lal, a physicist at the University of Utrecht, isn't holding her breath.
Of course, one of the problems you have in string theory is that there's all these many dimensions. Then you have to explain why you only see a few of them. So that would be wonderful if you could do that. But currently, that's too difficult, or no one has managed to show that.
Renate believes that the extra dimensions predicted by string theory are merely a mathematical quirk, and the theory itself is likely to be wrong.
Of course, it raises the question of, well, can we maybe do without these extra dimensions whatsoever?
Renate Lal's dislike for the extra dimensions of string theory is matched only by her passion to attack the same puzzle it was created to solve, the mystery of gravity. Einstein realized that gravity could be seen as simply a bending of space by massive objects. His theory of general relativity was a masterpiece of modern physics. But it left a serious problem unsolved. How does gravity affect space on the microscopic level?
So if you ask questions that have to do, say, with the very, very small, and that involves anything that has to do with gravity, so how do objects interact gravitationally on very, very short scales, then you need an extension of Einstein's theory, because it doesn't cover that range.
Renate has taken on that challenge. She's trying to develop new laws of gravity that apply even at the smallest distances, and she's testing them in computer simulations. She begins with a collection of microscopic points of space and attempts to stick them together with gravity. In other words, she is growing space. The last time this happened outside a computer was about 13.7 billion years ago. It was part of an event you've probably heard of, the Big Bang. Renate is working on a much smaller scale. But the microscopic universes she is cultivating have some very unexpected properties.
Imagine you're given a space, or just a piece of space, and you want to learn about what it is. And in particular, you may want to learn about what its dimension is. So one experiment that you can actually do to find out what the dimension is to let an ink drop fall in it and then see what happens, see how the ink spreads in the space.
In water, ink spreads into 3 dimensions. On a piece of blotting paper, it spreads into 2. But when Renate tested how things spread out inside her computer-simulated universes, the results looked something like this.
Watch what happens now. It filled out much less volume than we expected on small scales, and that's a sure indication that the dimension is actually smaller than what we expected. It's smaller than 3.
Renate's simulations look like they have 3 dimensions, but at root, they only have 1. If her theories of gravity are right, it suggests that solid space is not solid at all. Down at the smallest scales, it might be built from a mesh of one-dimensional lines. Is this the fundamental truth about how space is formed? Is one dimension all there really is?
So in the old days, one would think of the dimension of a space as fixed. I mean, just God-given, it's just there. But what happens then on very, very small scales? And there the story we find is totally different. The space appears to have a smaller and smaller dimension as you explore it on smaller and smaller scales.
Other scientists are not convinced Renato's one-dimensional universe is correct. Their bets are hedged on a universe with many extra dimensions. The truth is still elusive, but it's not out of reach.
It's a problem that we really want to solve. We really think there has to be an answer. It really tells us that something has to be there. And it could tell us that there's some really exotic underlying matter or physics or forces that we haven't thought about yet.
In the end, there is some theory. There's some simple, elegant theory out there that accounts for all of nature, for everything we see. And we feel like we could be very, very close to it.
So when you have shocking questions, it takes sometimes shocking ideas and answers to try to put your arms around this.
Are there 9 dimensions or only one? Is this hidden space warped or curled up in tiny loops? We don't know yet. But we can be ever more sure of one thing. The 3-dimensional world we thought we lived in is only what we see. Reality is almost certainly a lot stranger.